Hi, good afternoon. Today we'll discuss about nonlinear difference equation. Okay. I'm not sure if we can finish today, but if we can, next meeting will be a different topic. If not, we will continue this one. Okay. You can follow the slide in Pantera. Can you open that? Okay, so I will just share the screen. So while waiting for this class, I checked these pages and I tried to run the code and I think it works. You can see it now. Oh, okay. Difference equation supposed to be in mathematics. Mathematics calculus. Difference equation. Okay. So this is web, and this is scope web and bifurcation. So if you look at it, it will be like this. Does it work? Can you see? So we will learn about this. This is called logistic function. And this is called cobweb. And this is called bifurcation diagrams. And this is the Lyapunov exponent. Later we will discuss about it in the slide. Okay? Okay, so so far you have learned about linear and difference equation, right? Last meeting, and then you also have learned about second order and higher order dynamical system using difference equation. And today, this is like our last part, which is nonlinear dynamical system. So for this purpose, okay, I will just give a very simple model, which is called logistic. But from here, okay, I will introduce you with several concepts, okay, which is quite well known. So you will learn about chaos theory, right? You will learn about what is complexity, okay, and bifurcation. Okay, so this is what is called complex system. Complex system involve numerous interacting agents, several agents, whose aggregate behavior are to be understood. So meaning we don't know the application of this agent performance. Okay? So aggregate activities are nonlinear, hence we cannot simply derive from summation of individual component behavior. So look, try to find Santa Fe Institute in Google. SFE. Yeah? So Santa Fe Institute is it's a kind of university, but not really a university. It's an institute, okay, that dedicate themselves for complex system, to study complex system. Okay, there are more than 50 Nobel Prize winners in that institute alone, all over the world. Okay, so this is like one of the best institutes in the world, studying only about complex system. So with this, the one that we discussed today is like the beginning. And if you want, okay, you can also join Santa Fe Institute by joining their courses. It's free. Okay? If you are joining, you can also get the certificate from Santa Fe Institute. Okay. Warning, not so easy, but it's really free. And and the quality of their lecture and the quality of the online teaching is superb. Yeah, really very excellent. So you will not regret to join. Okay, I also get certificate last time. Yeah. Okay, so this is an example of both linear and non-linear system. Yeah? So when you have a dam like this, okay, and then the water going down here, the input is the water here, and the output here, right? And then you get the energy. So this distributing energy over time is a linear system. Okay? But what happened to this kind of avalanche? You know avalanche, right? So suddenly you have a snow avalanche, yeah, falling down. Okay. So this is an example of non-linear system. Yeah? Snow avalanches because of the small, okay, snow become wet, okay, and then accumulate, become large snow, wet, and then suddenly it become falling, okay, and create avalanche. So this is example of non-linear system. Okay. In fact, the turbulence of this water, okay, is also non-linear. So, okay. So when you said, okay, how if I model non-linear dynamical system, right? Difference equation. So again the same. Yeah? So if you look at this, the model is just like this. Yeah? Yk plus 1 equal a function of yk and yk minus 1 and so on. Yeah? So if you look at it in terms of the function, there is no difference between linear and non-linear. Right? It's just a function. Okay? But now you see this function itself is non-linear. Okay? So for non-linear discrete equation, analytical solution can only be found in a rare case. Okay? So if you can find certain equation that well known that people do not know the solution yet, and then you can solve, okay, then of course your name will be there forever. Yeah? Meaning literally forever. Meaning someone will refer your name again and again, 100 years from now. So this is still a very active research. Okay, and let's start with the story of Malthus. You learned that Malthus theory, right? In high school, probably you learned that over time, okay, in 1700 or 1800, so the population growth is exponential like this, okay, while the production of food is still linear like this, right? So, and Malthus said, look, this will create a permanent poverty, and at certain point here, probably the population of the world will decline. Okay. There is a possibility that the population is declining. But until today, so how many years? Like 200 years from Malthus, we haven't reached that point yet. Yeah? Because of the Malthus theory, humans start to gain understanding about this phenomena, and then there are a lot of new things invented. Yeah? These 200 years to overcome that food production. Okay? So apparently, in the last 200 years, food production is no longer linear also. Okay, so let's start with a simple growth rate. Yeah? So if you have a simple growth rate like this, you see this is the number of bird, and this is the population, right? And if you use system dynamic, this is like the CLD, yeah, causal loop diagram. This is the SFD, right? Stock flow diagram. Yeah? And if you put it into equation, this is the difference equation, right? So you have certain growth rate here, 1 plus A, yeah? And this is the population at times K, and then this is the population next year, okay? And you know the solution is this one, yeah? So, and then you get the population increase over time, right? So this is called unrestricted growth rate. Yeah? So then there are certain questions here. We want to make a long-term prediction about population growth. Okay, so look at this way. Why someone want to check the population growth? Okay, so if you know the population growth, okay, this is very important because you want to know whether the population will increase indefinitely over time. Okay, well, will it eventually die out? There are certain tribes, for example, in Native American, they actually die out not because of the attack from outside, but because of their marriage structure. You know, in Lentera, I gave you several books there. Okay, in the top you can check. Okay, there are several books on difference equation, and you can see some of these books have several examples. Okay, that create that merit structure in the society that eventually make them die out. So it's possible. So does the population increase monotonically or oscillate about certain value? Okay, is there any value parameter for which the population grow into chaotic, unpredictable way? Yeah? So this is some population question. So if you know the number of population, what is the impact? Okay, in this case, you will know, for example, how many hospital do you need, right? How many school do you need, right? Okay, how many public services that do you need in certain area because you know the population. If you don't know the population, then you cannot predict all this facility that you have. Say, suppose you want to create certain supermarket or mall in certain area, then of course the first thing you need to check is the number of population, right? So if no population, nobody will buy anyway. So even if you want to invest there, it's useless, right? So number of population is really important to know. Okay. So then the same model earlier, okay, which developed by Felhus in 1840. Okay. What happened? This is called logistic curve. So it said that every species has its own specific intrinsic growth rate. Yeah? So we call this mu. Okay? That can be achieved only under ideal condition. Say, for example, if population double each year, then mu is 2. Right? So the population growth is not constant as ideal condition, but diminishing as the food reduce. So what happened is, okay, in the population of rabbit, okay, so at that time, people see that rabbit was hunted by the foxes, and then, oh, pity, the rabbit is cute, right? Compared to the fox or the other animal predator that eat the rabbit, okay, seems like cruel, isn't it? So then they start to hunt the predator. Okay. At that time, they did not understand the meaning of ecology, so they start to hunt the predator. So they kill the foxes. Okay, and what happened? Because of that, the population of rabbit grew very much. Okay, and then the area, the number of grasses and the food for rabbit cannot cope with the population of rabbit, and more rabbit die because of hunger, and this is more cruel than eating by the foxes, right? They die because of hunger. Okay? More rabbit die because of hunger rather than killed by the foxes. So that is the start of people start to think in terms of system. Okay, if you just kill one of the the predator, apparently it will make the whole system broken. Okay, so this is also important. So now Verhulst, okay, proposed propose what is called logistic curve. Okay, logistic means dwelling place. So logistic growth is something like this. Okay, so this is the story behind. Okay, due to lack of space and food, yeah, competition between individual, maybe because of the predator, okay, maybe because of spreading contagious disease. Yeah. So there are certain limit in the growth of population. Yeah. Earlier we saw the growth is unlimited, right? So you will see exponential. Okay. But what happened is actually there is some limit. Okay. Or let's call this limit as the carrying capacity of the environment, L. Okay. So under which the maximum population which is sustainable over time. Okay, if you are the population is actually below L, yeah, below this capacity, okay, actually sustainable. It will grow exponentially. Okay, now in the beginning, the growth process there is enough resources, right? So the growth is exponential. Yeah? As the population approaches the capacity, what happened? The growth stop. Okay? It's the growth that stops. Now the population does not stop. Population is level. It's the rate that is 10 to 0. Okay? Now if the population is larger than the capacity, the growth is negative. The rate is negative. It doesn't mean that the population is negative. Okay? The population is level. Okay, so here it is. Okay, so this is the population, right? Is equal to the birth rate minus the death rate, and then the population currently. This is next year. Okay, and then there is some population square divided by the capacity. So actually, if you want, what I wrote here is the derivation, yeah, from this model. Okay, from this model, this one, right? This is the square, right? So from this model, and then we assume 1 plus r equal mu. Okay, so in that case, you will get this difference equation, right? So, and then from this model, we can simplify into this way, and then yk over L, let's call this xk. Okay, so remember, yeah, yk over L is become xk. Then you will have a simplified logistic map with this only one parameter here, mu. Again, this is still quadratic, right? So mu x times 1, and then mu x times x. And so this is squared. Yeah? Okay, so this is probably the one that we will use. Yeah? So, but time to time you remember, yeah, this logistic map here is exactly the same as this one. Yeah? But the difference is here you have two parameters, r and b. Yeah? In here you have only one parameter, which is mu. Okay, so but B is actually depends on mu and L. L is the carrying capacity a while ago. Okay, so we just simplified it. It seems like this is actually different model, but actually the same model. Yeah? Okay, so let's go to the assumption. Okay, so we know that unrestricted growth rate is only good estimate for a short period of time. Yeah? In the long run, the growth rate is not constant, okay, but changed by the size of the population. So let's assume there is a L, which is carrying capacity of the environment, okay, and then that means the environment can support maximum L number of species. Okay, so L is the unit is number of species. So if the population is less than L, okay, there are plenty of food, yeah, space, and the growth rate is positive. Now, if the population is larger than L, okay, the growth rate is negative. Yeah? If the population exactly the same as L, the growth rate is 0. So this is the assumption that we use to create a logistic curve. Yeah? Remember, in any mathematics, yeah, the most important part is the assumption. Okay? Because if you change the assumption, everything changes. Okay, so let's find the simplest growth rate function, okay, that satisfy those assumption. Yeah. So with this just a linear model. So say I have delta y here, okay, with this yk plus 1 minus yk. Okay. So with this model, yeah, r1 minus yk over l. So r is the parameter. Okay. So if yk is small, right, the population is small, so the growth rate, what will happen? The growth rate is, this A is the same as R, yeah? Because this is very small, 1 minus 0, for example, is A equal R, isn't it? Yeah? If yk is very small. So, but if yk is less than L, yeah, so this yk less than L, so this one is less than 1, right? This term yk over L is less than 1. So in that case, 1 minus yk over L is larger than 0, right? So in that case, positive growth rate. Yeah? So if yk equal L, so 1 minus 1, 0, so exactly, yeah? The growth rate is 0. So what will happen if yk is larger than L? So this term is larger than 1, right? So 1 minus something that larger than 1, so that means this one is negative. Yeah? So in that case, the growth rate is negative. Yeah? A is the growth rate. So this satisfies the assumption, isn't it? Okay. Okay, so yeah, if you want, this is just to algebraically derive, okay, the difference equation a while ago. So I think let's skip this part. Huh? This is just the revision. Okay, so just remember, if you derive that practice a while ago, this one is the same as this one. That's the lesson from that practice. Yeah. So this is called logistic difference equation, which is nonlinear, right? Why nonlinear? Here, the square, right? So it's quadratic. Okay. So the B here is called damping term. It will dump the growth of the population from keeping it from going to infinity. Okay. The R here is the unrestricted growth rate, right? So this is the one that growth, and this is the negative, right? To make it slower, okay? And the L is the carrying capacity. So in that case, we can simplify into just one equation like this. Equation with one parameter, mu. Okay. The curve of logistic is S curve. You see that? The curve is S curve like this. And if you put population over birth rate, you will see logistic, which is quadratic. Yeah. The same, yeah. Birth rate over time is also a kind of almost shape of the normal. Yeah. Where is it? Okay, so one thing you need to remember about logistic curve is this is called sometimes life curve. You know what is life curve? It represents the life itself. Okay? You look at this. When you are small, growth as baby is something in here, isn't it? Okay? And then when you are a teenager, suddenly your body grows very fast, right? I think there's a timer here. Okay. And then after that, suddenly your say you are 18, 19, okay, your growth, okay, no longer, your body no longer have certain height that you don't grow anymore, correct? Yeah. So the same thing with the company, okay. So not just human being, yeah. Company also when they start up, for example, the growth is linear, very small, here. So I remember when I started my referral is also linear, and then suddenly it jump, become exponential. So I thought it will go exponential forever. It's not. Yeah. After some time, it will start to slow down, okay, and become level like this. So what's the lesson? Okay. if you start to see your curve is starting to go down, yeah, to become a level like this, yeah, the growth rate is starting to be negative, what you should do? You need to reinvest. Okay, so this means old age. Nah? So you need to reinvest. Probably in the future, our body can be replaced, okay, with certain part of our body can be replaced. Then you start to invest so that people practically can live forever if you can replace some part of the body. So again, this is called S curve or life curve, okay, logistic curve. By the tangent, the gradient, you will know where you are in this over time. Yeah. Okay, so there are two driving force of the logistic. Why they are doing like that? Okay, one is drive to grow, okay, to go up, and then there is a limit to grow. Yeah, this is the capacity, right? So then, as the usual of any difference equation, there are three things you need to ask, right? One is the solution, right? Second is the equilibrium, isn't it? And then the third one is stability. Okay, so what do you think about the solution of that logistic equation? Is there any idea how to solve that solution? You understand the solution, meaning the algebraic equation that from x0 or y0, suddenly you get yn or yk. Okay? So equilibrium we can find, stability you can find, okay? But apparently for that simple equation, you cannot find. Okay, so imagine just logistic formula, just quadratic, we cannot find the algebraic solution. Yeah? So it's usually impossible to find the algebraic solution of nonlinear dynamical system. Okay, even the simplest one. Okay, and then you can simulate. Yes, you can simulate. Yeah? You can find the particular solution, but you cannot find the general solution. Okay, so there is no simple algebraic expression for that. Okay, similar to the affine difference equation, you can use the geometric, right? Series. This one you cannot. Right? So, and the equilibrium also not always exists. So, just be careful. Nonlinear system is very interesting. Okay. So analogy is a prime number. So one can say, oh, all odd number, odd integer were prime. Yeah? 1, 3, 5, 7. 1 is not prime, but okay, exception. And then you said 9 is not prime. Okay, that's exception again. And then you will say, see, 11, 13 are prime. Okay. And then 15 not prime. Oh, exception again. So many exceptions, yeah. So practically, this is a wrong hypothesis, right? So it's not a true pattern. Okay, so the point is, no matter how many values that we computed, yeah, no matter how convincing the pattern that you talk about, we still make no certain conclusion about the next value. Right? So many people will find certain pattern, say a pattern, but when one value disagree with the pattern, they tend to ignore exception. Yeah? So instead of looking for better pattern. Yeah? So the same thing. Okay, logistic equation is the simplest, right? First order only, right? Non-linear dynamical system, and yet we cannot find the algebraic solution. Okay, so how much more with the more complicated non-linear system? Okay, so that means to solve the non-linear equation, probably simulation is often the only way. The only way. Yeah, that means you use the recursion. Yeah? Simulation means you use the recursion. You cannot find a simple algebraic solution. How about the equilibrium? Equilibrium points, so this is the state, right? And the stabilities will provide some information about the behavior of the solution. Okay? So in my model, in say pedestrian simulation, multi-agent system, okay, we always use this equilibrium point and stability. Okay, how we will apply this. Okay, so for example, I want my agent move from one point to the next point, right? So from certain, let me throw in a pen here. Say this is my origin. It will go to destination here, right? So in that case, I need to design. Okay, I need to design this agent so that it will move that way. Okay, and for example, there is a wall here. Okay, and there is a wall here. For example, okay. So that agent should not be go inside that wall, right? Okay, and to make that point, okay, I would say there is a simple way to do. Okay, if in magnetic force, if plus and plus, what will happen? Repulse, right? If plus and minus attracted to each other. Okay, so then you can set your agent. For example, your agent is plus. Okay, and this is the destination. So what you will do with that destination? You will make it negative. Okay, so that this agent will move here, yeah, toward this destination. How about this one? Okay, so that the agent will not go to the wall. You will put plus here. Yeah? You will put the same sign, okay, plus. So it will repulse. Okay, so this basically you create equilibrium point. The one that you set here is the equilibrium point. Yeah? Attracted mean stable, right? Repulse mean unstable equilibrium. Correct? So with this you can design anything. Okay? So for example, you are telling, okay, I want to see the attraction is not just space here. Maybe the attraction is actually economic attraction, for example. Then you can design that. Okay, so or motivation attraction, you can also design that. So based on the equilibrium. I hope this is an important clue that you can actually design anything based on the stability. Clear, yeah? So that's why equilibrium point and stability is important to study. Okay, because with that you can design anything that you want. Right? So now equilibrium point is sometimes called steady state or fixed point. Okay, what is that? There is no change, yeah? Absent of change. So constant solution, yeah? Steady state solution. So when the system start in a steady state, like in Markov chain, right, it will remain there forever. Okay. So now how we will find the equilibrium point? Analytically, you know, equilibrium in this is the same as this one, right? In that case, I'll just give another name. Okay? So which not depend on n, not depend on the time. So let's call this y star, right? So then you know that equilibrium point means the y star. This is now become y star, right? And then inside here also become y star. So become this equation. Yeah. So because you know left and right is the same as y star, then you can easily solve this one. So equilibrium usually easy to solve. Okay. So this is an example. So I have this equilibrium. I want to find the equilibrium. So what I will do is just make the x star. Yeah. Because this is quadratic, right? So then you can get the two equilibrium value. Yeah? One is 0. The other one is at capacity. Okay. The equilibrium is at capacity. Okay. So suppose you have a logistic equation with R is 0.2, L is 8. So you're supposed to be able to find the dynamical system equation, and then you need to simulate this one. Do you want to practice or you want to skip this?
Using Excel.
Yeah, it's okay. Excel or use, of course, the equation you need to.
Can we try like
Oh yeah, okay. Please try. Okay. So here is the equation. Okay, but you need to put it in. Okay, try. So we have R and we have L. Okay. So in that case, what is the value? The equation is this one, the one in yellow. Okay. So you know R, right? This value R and L is given. Okay. So because you know R and L, you can calculate P. Okay. You also can calculate mu. Okay, and then you can draw y0 is given, so you can put in, and then you can draw. Next up. Once you make it, you can share your screen. So what is the equilibrium value? And what is the stability of its equilibrium value?
Wait, can you help me? I'm kind of
Sure.
confused.
Okay, you have y0, correct, yes. And then the equation is
1 plus r
okay. Wait. So
multiplied by yk. Since
is
it's yk plus 1, so yk is 0 minus 0.1. Is it correct?
wait. So 1 plus r. Let's give a name if you want. R, P, and mu. You want?
Okay, wait.
So that one is R underscore R underscore. Okay. And then that is P underscore. Okay. And then that's mu. Okay. And then the y0 is the same. And then this one is 1 plus R. Okay. And then multiply by earlier. Right. Minus P underscore, right? Multiply by the earlier square. Correct. Okay. Very good. Yes.
So, oh, okay.
Okay. Then you just copy it out. Okay. Okay. So that one. Okay. Very good. So this is the uh, now you can copy. Okay. You can copy this. No, the column B only. The value column B down there to more to the right. Okay, 4 times. 2, 3, 4. Okay. No. 4 times. No. 1, 2, 3. 1, 2, 3. Maybe 6 times. No.
Oh, 6 times?
Yes. 6 times. Okay. So now you change the. First, you need to calculate what is the equilibrium.
Now I change the value of the y0.
Okay. You change the value of y0. Then the other one is 6 and 10, right? Okay. And then now you can plot.
Oh, 4 of this.
From the x is this one, the 0, 1, 2, 3 until 18, and then the y is all.
The x is, sorry, I
Yeah,
was slicing.
from A to E, highlight everything, you select everything, and then you plot that one, x, y chart. Yeah, the chart x, y. Oh, very good. Okay, now you can start to see. Right. So there is another equilibrium there. Okay. Actually, in the middle of between the green and yellow, there is another equilibrium there. Correct?
Between the yellow and the,
Green. Actually, there is one more. If you start with, say, if you expand this with one more line in column F, for example, with you put it 8 there. That is equilibrium, right?
yeah, everything is, oh,
Okay. So the same thing if you put in column G, you start with 0, for example. two equilibrium, which is 0 and 8. And if you plot that, the two F and G together, then together with a while ago. So yes, that equilibrium is, which one is stable, which one is unstable?
This one is stable.
Correct. Yeah. 0 is unstable in this case. Yeah. Yeah. So you can see the stability, right? Okay. Very good, very good. Is there any question about this? I think it's clear. Yeah?
No. Oh, so it's very similar with the one we learned the first time, right? So
Correct, correct. It's just the same,
yeah.
just different equation, right?
Uh,
So last time this is not, that is linear, so this is non-linear. Okay, that's the only difference at this point. Okay, so let me continue. So this is the equation, right? So you know the equilibrium is actually always 0, right? Always 0 and L. Is that correct? There are two equilibrium, yeah? Y is 0 and then Y equal to L. Okay? So, but when you put it into mu later, that is totally different equilibrium. Yeah? Okay, let's do that. So, okay, I have, let me open this. Oh, okay. So you see the B is 0.2 divided by 8. Okay, and then this is the dynamical system, right? And then if you want to find the equilibrium, this one you put into F of Y star, okay, which is supposed to be equal to itself, correct? And then you can get, you solve this quadratic equation, you get Y star is 0 and Y star is L, of course, right? And then from there you can symbol it. Yeah? This is the one that you symbol it a while ago. Okay? Oh. I need to come back. Okay, very long. Come back. Okay, so now there is another way to find equilibrium point. Okay, this is called cobweb technique. Okay, so the equilibrium point is the intersection of two graphs, okay, with this just a straight line. What is that straight line? The straight line is meaning that if this is yk or yn and this is yn plus 1, that straight line means yn plus 1 equal to yn. That means this is the equilibrium point. So everything in this blue line must be equilibrium point. And then your curve, for example, any nonlinear function, right? You also plot in yn and yn plus 1. Okay, you plot that. And then anything that actually intersect with this blue line, okay, that blue line is yn plus 1 equal to yn. Right? That means this is the equilibrium point. Is this clear or not? So again, this is a technique to find equilibrium point. Okay, how to find? Just draw between, okay, yn and yn plus 1. So in your Excel a while ago, every yn and yn plus 1, you just put it to, side by side. Then you can plot. Right? So question is, what happens if you slightly perturb y from the equilibrium point? Will the object return to y star or move away? Okay? So this is called stable, and you know this is unstable equilibrium, right? Okay, so now if you want to find the stability from the cobweb, you can also do that. Okay, first you draw yn plus 1 equal to function of yn. So, and then you draw this f in the yn and yn plus 1 plane, the one that I drew a while ago. Yeah, this is the one that we draw. And then what you will do is, from any initial value, y0, you draw vertical line. Yeah? To obtain y1, so you draw a vertical line through y0, so that it will intersect the f at this point. Y0, Y1. After that, you draw horizontal line. Again, you draw vertical line, horizontal line, vertical line, horizontal line, and so on. Okay. So if you continue this process, it will meet eventually in the equilibrium point, in the diagonal. Okay. So something like this. You see. So if you start from YB here, you draw vertical line until the curve, right? The red curve, and then go to the equilibrium, and then go down, and eventually it will reach to this equilibrium. That means this equilibrium is attracting from YP, right? But when you change the Y0 into YA, okay, it will go here, then go there, and so on. It will go here. That means this, again, equilibrium is attracting. How about this equilibrium? Repelling, right? In this example, this is, you see, anything that near this equilibrium is always repel, going away. Yeah? And going to where? Going to this one. Going to this one. Can you see that or not? So cobweb is basically trying to show, okay, how the movement of this initial value that you set, okay, into the equilibrium. Of course, what you want to set is near the equilibrium, so that you will see how they behave. Right? So you start from here, it will go here, or it will go to the other side. So you know where the equilibrium will go, where the movement will go, which equilibrium it will go. So application. Right? Application a lot, but I can give you like this. So, in a interpersonal relation, okay, say you with your friend, okay, so equilibrium means there is certain stability, okay, between you and your friend in terms of the relation, right? So, if you are too close with your friend, probably it will create friction. Okay? If you are too far, you probably will miss each other, and so on. So again, you will know about it when you try, okay, by setting any point of distance. So this is not real distance, but probably social distance or psychological distance that you can put. Okay. So these are example of application here. So again, this is definition of stable and unstable. You know it already. Okay. And this is neutral or semi-stable. Yeah? You also know. Last time we discussed about this. Yeah? So now, this is the criteria to be semi-stable. Yeah? Semi-stable have two sides. One is called semi-stable from above, and then the other one is semi-stable from below. Yeah? It is attracting and repelling from different sides. Okay, so if you want to do cobweb in spreadsheet, so okay, so say this is your mu and so on. Okay, what you will do is you just copy this equation exactly, and then you copy every two. Okay? Every two of this you copy, okay, down, okay? And then you can you can create a cobweb like this. Yeah? But if you use Python, you just get the code, okay, and then copy and paste, you can get the cobweb. Yeah? Using that, what you need to set is the initial value, okay, and then this is like the solution. Okay, so let me show you. Can you see my screen? Excel.
No, only your PPT.
Oh, okay. Let me share different way. Okay, now you can see, I hope. Okay. Okay, this is using this equation. Okay, maybe this is better. So this is using y0 and this is using mu. Okay, so it's the same, but I use a different equation. So if you look at this, okay, this is I start with the equation is the one that I showed you a while ago. Using x. This is the equation. Can you see? So this is the equation that I put here. Okay. So I use mu. I have y0, and I can set dx. Dx is 0.01. It's up to you to decide. Okay. So say I have mu is 0.8, right? And then you can set any. So you see the equilibrium is in 0 because this is the straight line, right? And then anything that you put, for example, your I0 is 0.5, it will go to 0. Yeah? What happened if I put 0.9 here? Okay, again, go to 0. You will see it will go to 0. So the solution is like this, and this is the cobweb. And interesting things here is when you start to make a mu is larger than 1, okay? 1.2, for example. Okay. You see it will go to this equilibrium. So, yeah. Or let's make it 2.1. You can see that clearer now. Yeah. So this one, now you have two equilibrium, right? One is 0 and the other one is this intersection between blue and red. Okay, and you start from this y0 0.9, you can see it will go to this equilibrium, not 0, but to the second equilibrium. Yeah? But if you start from, for example, 0.1, again it will go to the second equilibrium. Yeah. So now what happens if your mu is actually 3? Oh, yeah. You can see the solution. Okay, it starts from here, right? And then it will become oscillate, right? That oscillation is actually around this equilibrium. Yeah? It will never reach equilibrium, okay, but it just go around and round near this equilibrium. Right? Okay. And what happens if you have a 3.5, for example? Oh, what happened? You see, yes, you still have two equilibrium. Okay, say I start with certain number, 0.1, for example. But if you look at the solution, okay, there are certain value that repeated. You see, right? So as if there is a certain cycle that it will repeat to that. So there is certain number of cycle. Okay. Right. The number of cycle will increase. Okay. So if I put say 3.6, for example, again the number of cycle going up. Yeah. Right. So there are certain value that repeated. Okay. And if we increase, say, 3.7, wow, okay, the number of cycle is now is look like what is that, the heart already, right? So there are certain cycle that repeated so many times. Okay, so that is
Sir,
yes.
so if we use the analogy of the rabbit population, so if the growth rate is 3.6, so
Mm-hmm.
it will repeat the cycle for several times.
Correct,
Similar.
correct, correct,
Okay.
correct. So it will go up and down at certain value, and then
Okay.
certain cycle. Apparently, there is a certain cycle. Okay, so then look at it this way. Look, our model does not change, right? It's just the same logistic equation, just the quadratic a while ago, right? Exactly this equation, okay? All the one that we change is only the initial value, and in fact, the initial value I did not change. All I need to change is the mu, isn't it?
Mm.
So it's sensitive to, because of this mu, there is certain parameter mu that actually will create different behavior, right? Uh, that is very interesting. And in fact, that behavior that changed because of the parameter, okay, uh, was found around 1970. That's amazing. You know, remember I told you in the beginning is about the story about Malthus Verhulst. Yeah, I even put the year, right? From Malthus to Verhulst, how many years? Yeah, and then from Verhulst to later Fakenham, you can see 1970, right? So it's kind of 100 years, right? 100 years to find that. Okay, that actually parameter is sensitive to parameter, yeah? And sensitive to initial value also later. Yeah? So this is very interesting. Okay, so yeah. So if you look at this, yeah, certain parameter value, there is some kind of uh, chaotic behavior. Yeah? Some certain value of mu a while ago, it will create a, see, this is a chaotic. Okay, what is chaos? There is certain pattern that is unpredictable, right? You see, okay, there is some cycle, but there is no cycle also sometimes, and then the length of this is not the same, right? See, this is suddenly become longer, right? So there are certain pattern that is chaos. So what is chaos? That's the next question, right? Chaos is basically deterministic random. What's the meaning? You have a random behavior, okay, or apparent random behavior, which come from equation with this no random number at all, isn't it? We don't even put random number here. Right? This is exactly the same logistic equation, but the behavior suddenly become random, even though there is no random at all. Random, no randomization, right? Exactly the same equation that you put there. What you need is just change the parameter. So why there is some kind of random behavior, okay, out of deterministic. So if you want to define it simple, yeah, what is chaos? Chaos is deterministic random. Okay? So again, you can determine the stability using web a while ago. Yeah. So check the gradient. Yeah? This is the first derivative. Okay. If the first derivative is less than 1, okay, it's stable. Yeah? If the first derivative is larger than 1, you know this is unstable. Okay, from the gradient of this you can start to see. Yeah? So with that, because of that web, now we can see the criteria. Okay, so if you have a this non-linear dynamical system, and you know y star is your equilibrium value, so you put it in, this y star into that equation, right? And then what you will do, you take the first derivative, okay? And then you take the absolute value. Okay? If the absolute value of the first derivative of that equilibrium is less than 1, you know the equilibrium is stable. Okay? If larger than 1, this is unstable or repelling. Okay? But if it is exactly 1, you don't know. So in conclusive, okay, then you check the second derivative and the third derivative. So if exactly 1, this is more complex. Yeah? So you need to do first derivative and second derivative to get this criteria. Okay. So if this is 0 or not 0, yeah? Second derivative is 0 or non-zero, and then if 0, you need to check the third derivative. Yeah? So if the second derivative is not 0, then you know it's semi-stable, yeah? Either from above or from below. Okay, and if exactly negative 1, okay, if exactly negative 1, remember that one is absolute value, right? That means can be positive or negative. So if exactly negative 1, then you take the, again, second and third derivative, you calculate this function g to determine the stability. So this function g is sometimes called Schwarzian derivative. Anyway, so this is the stability and the behavior. So you can see if the first derivative is larger than 1, is exponentially growth. Yeah? If 1 is usually constant, and so on. Okay. So this is what is known to be the behavior of that logistic equation. Yeah? Okay, yeah? This is logistic equation only. This is just the practice to get the equilibrium. You already did. And then, oh, you want to calculate the stability and equilibrium point? Or you want to skip?
We can try just to
Okay.
make sure that I understand.
Right. Because this is cubic, so can you make it? This is 3 equilibrium point. Yeah? So, so you put y star here, and then y star, and then y star cubic. Right? And then you calculate the solution of cubic equation. Okay, so you get the solution of cubic equation like this. So what you will do, of course, you will do this. Yeah? First derivative, second derivative, third derivative. Hey, we are in difference equation, but you still need the continuous differential equation, okay? You still need to do the calculus. Okay, so and then you put the equilibrium value 0, for example, and then you get the Schwarzian. So this one is 0. So if you put this one 0, you know this is equal to the third derivative. If whatever it is, still 6, right? Because there is no number. Even if you put this y is 0, because this one had no y, so the third derivative is always 6, minus 6. The second derivative depends on y, so if this is 0, this is also 0. Right? And the Schwarzian have no first derivative, but that depends on this value. So the first derivative, if you put this one 0, what will happen? This one become -1. So if you know if this is -1, you need to calculate the Schwarzschild. Okay, and because you know the Schwarzschild is 12, okay, you know this is the value. So what do you think?
So far, so good. Will our like this later?
Ano? What?
For our exams, would it be something like this? The questions.
Yeah.
Okay.
Look, don't worry about exam. Exam is basically open everything, right? And it's just testing that you have it. So it's just exactly the same as.
Your exam is tricky because several the
Oh
questions
yeah, several questions.
several answers. That's
Yes.
why.
Yeah, the difficulty is only because of several questions. But usually I put exactly the same as this one. Right? So if you just practice, you know, and then you can answer it easily. Okay, so next. Uh, if you use this logistic equation instead of the y, right? So you know it will exist only if the mu is positive. Yeah? If mu is 0 or negative, it doesn't exist. So this is the equilibrium value. Okay, so 1 minus 1 over mu and 0. Okay, 0 is always there. And these are the stability. So okay, so this is the equation, and this is you get the first derivative, right? And if because this is we know x1 is always 0, so then you know if it is stable if and only if mu is less than 1. Yeah? And then the second equilibrium, yeah, is stable if and only if between 1 and 3. Mu is between 1 and 3. That's why I tried a while ago, right? Okay, less than 1, yeah, 1 and 2, and then larger than 3, right? Okay. So then the next question is this. What happened when you have mu larger than 3? Okay, so I supposed to give you assignment to calculate, to create the program either in Excel or in to do cobweb, yeah, because this is very important. With this, you can solve your test later. Without this cobweb, if I give you the equation in the test, you will not be able to solve it, right? Because of course I will give different numbers from the slide. So look, what happened when your mu, yeah, the parameter mu is above 3? Yeah? At certain point, there is an oscillation or period of 2. Cycle, okay, up and down, period of 2. Okay? And then that stable oscillation is periodic behavior, right? And then you will see something like this. Yeah? This is less than 1, right? And then when you are between 1 and 3, see, yeah, it will go here. And then when you put it larger than 3, you see here there is a going up and down between 2 cycles. Yeah? It will reach the 1 and 2. Here is the 2 cycle that repeated here. Yeah? And this is the cobweb. Right? When you, this is the exactly 3.2, okay, you will see this behavior. Okay. So this is the equilibrium value. and this is the exactly 2 cycle. Can you see that? Okay. Here is the cycle to go to the equilibrium, but not exactly equilibrium. So it will just cycle around the equilibrium. See, up and down, up and down, and that value is exactly this one, 0.5 and then 0.799. Okay, and then the next question is, okay, there is a cycle. We found there is a cycle. Okay, so that cycle have period of 2. Okay? Then you check, yeah, if it is stable or unstable. That cycle is stable or unstable. Okay, to know that, again you put all this value, okay, the equilibrium of the fixed point of the 2 cycle, and then you put it inside, you multiply everything of the first derivative, right? And then you take the absolute value. Yeah? If this is less than 1, it's stable. Otherwise, if larger than 1, it is unstable. Again, if exactly 1, we don't know. Okay. The existence of the 2-point cycle, okay, in the cobweb, you can see graphically based on the intersection of the 2 curves. Okay. So when exactly this one, you see, every n plus 2, okay, there is an n, so there is some kind of intersection. Okay. Then you can see there is some assistance of the 2 points. Let's plot this. Okay. This is the derivation to get the 2-point cycle. Okay, and it say that, look, if we derive it that way, you will know this is the value of mu. Okay, so then you can get the 2-point cycle based on this. Okay, this mu that will create this 2-point cycle. Okay, so example, okay, you want to try this one on your own, go to this website. I will put in the chat.
Sir, can I go to the restroom for 2 minutes?
Yeah, okay. So let me stop. Okay, so just copy this code and try to run it. Is it running?
Okay, wait, give me a moment. My spider
Sure,
took
sure.
a while.
Yeah, there is also Jupyter notebook there. So you just okay. So this is the website. Okay, so this is the address. This is for Leafy. And there is Jupyter notebook there also, so you can also try, yeah, in GitHub. Yeah. So basically you can get this one. So this is, the logistic equation is R and X. You see that the R is your mu, right? In the slide is mu, so here they put R. Okay, so this is the R and this is your X0. Okay. So with that you can, R is the mu in my slide. Okay. So you practically create that cobweb.
So the values that we are able to change is the
If you put plot system, right? The plot system is R and X0. So, and you can put as 10 or whatever number. So only the first two numbers that you need to change. The R and X0.
is this okay?
Hmm.
I have an error here.
Oh, that error is easy. You just comment that because that is for Jupyter.
Oh, okay.
That comment, you just Control F, Control 1. Okay, okay. Okay. So the line from 54 below that letter 54 and below, you can just comment that first. No problem. Okay. Okay, and then you plot that one. So I think you just run this.
Okay.
So uncheck the inline. Okay. You can uncheck the inline plotting so that you can also get. Okay. Otherwise, it will go inline. In the tool preference, if you want. In your spider, tool preference, and then graphic, I guess. IPython console, and down there is a graphic. Is that correct? There, graphic. Oh, it's already inline. Automatic. Okay, just put it automatic. Put it as automatic. Okay. And when you run again, I think it will supposed to be going out. No,
No, it's okay.
it's okay. It's just showing where to render, right? Okay, so you get this.
So
Yes, sorry.
it's okay. Yeah, you may continue.
Yeah, so with that, you can change the R, right? So you just put plot system, and then you can, at the bottom of your code there, at the bottom, this one is the R and Y0, right? Or X0. So that one you can say 3.2, what will happen if you put 3.2? Supposed to be plot system 3.2. Okay, so if you run that, it's supposed to be uh, 2 cycle, isn't that? No? Supposed to run to be a 2 cycle. Okay, and you can change the value. Okay, now try to do 3.84. 3.84. The R is 3.84. And then, okay, and then the initial value is 0.1494, for example. 1494, okay. Yeah, that one you can put 100 or 10, is up to you.
100.
No, it's okay. I mean,
Okay.
oh, can you see? Okay, there. Oh, there are 3 cycles, right? Can you see the 3 cycle? Let me annotate in your. You see, this is the first, right? And then this is the second. This is the third one, right? Sorry, this is the one, right? This is the third one. Yeah. This is not. Can you see the intersection between the cobweb with the line, with the diagonal line. The cobweb with diagonal line. That form the cycle. Okay.
Sir, why? I don't understand. The higher the mu means like the higher the growth rate, right?
Hmm.
Yeah, but then why does the higher the mu, the fewer uh, the cycle?
No, the higher the mu is the larger the cycle. The larger
Oh, but
the
this one 3.5, we have like multiple cycles.
3.5 is not really multiple cycle. This is kind of chaotic.
Oh, okay, okay.
Okay. So uh, exactly, there are certain behavior of certain parameter value that will create cycle. The other one will create chaos. The other one will become deterministic. So now, depending on the parameter value, okay, suddenly you will have different behavior. And this is interesting. Okay. This is what is called complex. Okay. Life is complex. What is complex? Right? We call this the edge, the edge of chaos, the boundary of chaos. Okay? The edge of chaos. There is a book called, you can find in Amazon, The Edge of Chaos. Yeah? That means life. Life is the edge of chaos. That means complex. Two things. Yeah. One is regular. Okay? There are two parts of regular. One is very dull, okay, just linear. Yeah? The other one is cycle. Cycle is regular, correct? Cyclical behavior in the here is three cycle. A while ago was two cycle. Yeah? Cycle is regular. Uh, Linear is or constant value is regular. Okay, and then there are certain thing is random. Right? That is called chaos. Correct. So, but there is certain things that is called complex. What is complex? The edge of chaos. Okay? The boundary between regular and chaos. That is complex. That is the balance. Okay. That's why finding that balance is not easy, but that's why they study complex system. Okay, with more than 50 Nobel Prize winner there, right? But at the same time, you can see how important it is. Okay, this nature that you live in right now is complex. Right? Why the Earth is always moving 24 hours in cycle? Right? How that can become a balance? How the economic work actually? Okay, so these are complex. Eh? How human body as living being, okay, can regulate itself, right? Your temperature is a certain degree, isn't it? If you are 30 degree, you die, right? If you are 42 and above, you die also, right? So there is certain balance that you are. That is complex, right? So this is very interesting. Okay, at least scientifically, this is interesting. Okay. So I just want to introduce you that at least you are aware of these scientific things. Okay. Next, you can try 4 cycle if you want. 3.5. Okay. Check my slide. Practice 6. Okay.
Okay, practice. Oh, 3.5.
Yeah, the R is 3.5, yeah? And then that one is 0.874997.
Oh, wait, how do you come up with the numbers? Like, do you
Oh,
check it
that
before?
one I check it beforehand. Yeah? I check it one by one
Uh,
manually.
understand.
Oh, there you get that, right? 4 cycle.
Oh, this one is the initial value, right?
Correct, that's
So,
the initial value.
okay, so this is the mu, this is the initial value.
Correct. Right. So if you put exactly that value, you can see the cycle clearly. Yeah. If your initial value is not exactly that, the cycle cannot be seen well. Yeah, there is still 4 cycle, but cannot be seen well. Yeah. So it takes a lot of time to try this number.
That's why I was like, oh, where did you get numbers?
Okay. Yeah. Okay. So the discussion is cycle, right? So let me share again. Right. So uh, everything in life, there are certain things that are regular. Okay. There is also certain thing that is regular in terms of periodic, yeah? In terms of cycle. So the periodic orbit of the Earth, there is night and day, the season. Okay. The time itself is basically based on cycle, right? So now, go to the next topic. Yeah, you understand cycle, right? You know how to find the cycle in bifurcation in cobweb a while ago, right? Okay. Now, bifurcation is the next theory, okay, based on that number of cycles. Okay, what is that? Bifurcation say like this: small input does not always lead to small output. Okay, uh, we often hear the say the straw that broke the camel's back. Do you know the meaning? Okay, the camel you put a lot of straw, yeah, and then the camel is too strong, no problem. Okay, at certain point you just add one straw to the camel, and then suddenly the camel break down. Okay, yeah. So what is this? Bifurcation theory is a study about breaking point. Okay. A lot of things in life, okay, in many applications, actually there are certain qualitative behavior of the system change that break the system. So, for example, the building, okay, there is a column, right? Okay, when you add the load into that column, okay, no problem, it's just bent, okay? And then up to a certain point, it will break. Okay, the building collapse. Okay. Another example, sugar. Do you know diabetes? Right. So when you have a number of sugar in your blood, okay, increase at certain point, no problem. Okay. But up to certain threshold, this is biological threshold, and then suddenly you become diabetes, and then cannot come back, right? So if you have a stick and then you break it, so there is a breaking point, yeah? Or there is a metal rod, okay, you can put up and down like this, become hot, eventually will break, correct? Yeah. So that is a question is why, right? So, and how many times probably, yeah? So yeah, these are, I put several examples, okay? Melting point of the ice, okay, between ice and water. Oh, for a long time, yeah, human cannot go out of the outer space, right? Go out of the space. Okay, why? Because apparently there is a certain breaking point of the rocket. Yeah? If the rocket exceed that threshold, okay, that break the gravitational force, right? It will go outer space, and otherwise it will come back to the earth. So there is a threshold. Okay? As look, why this is interesting, because threshold is non-linear, isn't it? On itself is like a decision point, right? But look, our system is like continuous system. Suddenly there is a discontinuity in that continuous system. That is the one that make it interesting. Yeah, something unexpected happened. So, is there any bifurcation, uh, maybe behavior that you ever see in everyday life?
Almost everything has a breaking point.
Breaking point, like what? Example.
Uh, like school workload. At a certain point, students might break.
Yeah, it's too much load, right? And then the student will break, and then okay. So, for example, you're a very patient girl, okay, and you get a lot of pressure from outside, so you have no problem. But up to certain point, suddenly you break, and then you become angry, for example, right? So there is a breaking point even in psychology. Okay, so diagrammatically is something like this. Okay, this is your value, and this is your parameter. Okay, so lambda here is the parameter. Okay, so uh, up to certain point, there is no problem. It's like linear. Okay, and then suddenly, what is this? Suddenly you have two cycles. Okay, this is the equilibrium point, right? Stable. Okay, up to certain point, like a while ago, 3.2, right? Yeah. In 3.2, suddenly you have two cycles. And then if you continue to do that, you increase the parameter, yeah, the mu. It's still two cycles, okay, up to certain numbers, and then suddenly become four cycles. Okay. So if I throw it 3D, something like this, eh? Going the ball is now become decision point, eh? Either to the left or to the right. So that's the bifurcation point. Is the decision point, the break. Okay. So again, if you want to do in Excel, you can also do that. Okay. So remember, yeah, the horizontal axis here is actually the parameter mu. So we set 0 to 4. Okay. And then the vertical axis is the equilibrium. Okay. Now this line, so 0 to 1 is the stable, yeah, attraction point. Okay. So the bifurcation diagram, you can copy and paste the down in that website a while ago. You can draw the bifurcation diagram. Yeah. So bifurcation diagram is simply the mapping of the attractor points. Okay. So uh, the value of the parameter will determine the existence and the stability of the steady state, isn't it? So by definition, bifurcation is a change in the number and the stability of the steady state at the parameter change. Okay, so that means the bifurcation parameter is a parameter that is capable of causing the change, the threshold. Okay, so that diagram is just a summary of the effect of parameter variation and the stability. Yeah. So this is, remember, the drawing is this way, right? Up to certain points, and then you have two cycles. Yeah? And then say between 1 to 3, okay, you will have a solid line like this. Okay? And when your value is again at a certain point, you have two cycles. Okay? And then from two cycles, you have four cycles, and three cycles, and four cycles. Okay? And then suddenly we have eight cycles, and so on. So these are the number of cycles eventually become infinite. Okay? So as you increase the parameter, okay, you will see number of cycle increase. Yeah? So say from 2 to 4, 8, 16, and so on. Okay, and Feigenbaum is a physicist. Okay, he learned that okay, for a long time the study about logistic curve is parameter is between 0 and 1. Okay, between 0 and 1. That's why there is nothing new in that logistic curve for 100 years, right? And then suddenly in 1970, I forget the name of the paper. I read that paper before. So suddenly someone found a chaotic behavior when you go above 3. Yeah? The mu is above 3. Okay, and then Feigenbaum found certain different pattern. Okay, the cycle pattern of this. Okay, it's increased by 2 exponent to the n, and then the window of this parameter will eventually convert, and that conversion of that window, for example, if mu about 3, okay, the period is 2. Yeah? At mu about this value, 3.44 something, the period is 4. Yeah? And when mu is about 3.5, the period become 8. Right? When mu is about 3.5 something something very long like this, the period is suddenly become 16. So this is the bifurcation parameter, right? So, and if you have mu is 3.56999, suddenly the period become infinity. So this is the edge of chaos, right? So then he do this. What he did is just taking the difference and then take the ratio. Okay, and this is the distance between the bifurcation, which is shrinking, and it will of course convert to certain number. Right? That number is now called Feigenbaum number. You can check in Wikipedia, I guess. Okay, so its new bifurcation will appear, okay, about 4.6692 times faster than the previous one. Yeah. So this is the speed of bifurcation. Again, we study about complexity here, right? So then it becomes Feigenbaum constant. Yeah. So Feigenbaum constant is important because it's related to the edge of chaos. What is that? Complexity. Yeah. Anything that smell like complexity is very interesting. So look at it this way. Yeah? So there is a fixed point of mu, and then there is some periodic, and then there is some chaos, right? At certain value, which is here, so this one become the edge of chaos, which is complex. So what is chaos? That's the next topic, right? What is chaos? So chaos marked the end of the classical science. Yeah? So for centuries, okay, the logistic equation from Verhoeven a while ago, okay, we thought that it's already completely well understood for 100 years. Oh, the name is Robert May. I read that paper in Nature. Yeah? In 1973, okay, he found that chaotic behavior hidden in logistic equation. Yeah? In fact, the chaos itself has been discovered by a very well-known mathematician called Henry Poincaré, okay, in 1893. Okay, he tried to solve a three-body problem. Remember, two-body problem solved by Newton, right? Newton gravitational problem. If you have moon, and so the Newton gravitational equation, that is two-body problem. And then there is somebody, I think the king of one country, okay, making competition, okay, who can solve the three-body problem. Okay, so Henry Poincaré proved mathematically that there is no solution for three-body problem. Okay, so because of that, it led to experimental chaotic, chaos in mathematics. Yeah. So look at this way, meaning when your growth rate is sufficiently large, right? right, in terms of that population a while ago, that population will grow at random way. That's the meaning of that growth rate to chaos. Yeah. So it has been proven that the emergence of certain art cycle are predictor of chaos. So what is chaos again? A dynamical system that extremely sensitive to initial condition. Okay, that give rise to the solution of large random fluctuation with no inherent periodicity. So the periodicity is unclear. Okay, so one of the example found by Lawrence in 1963, they call it stress attractor. Okay, this is three differential equation. Okay, I did not put it here anyway. So you can check. Okay, look, stress attractor of Lawrence. Okay, in Google. It's basically three differential equations that lead to chaos. Okay. He studied about weather forecast, meaning this is where the term of butterfly effect, So it said that butterfly flapping in Brazil, okay, can create the storm in Indonesia. Okay, so the initial value matters because you just change a little bit, yeah, initial condition, the y0 or x0 a while ago, okay, and then suddenly it will create a random fluctuation. Okay, so I give you example here. You can try, okay, in your logistic equation, this one, 3.57 up to 4. Yeah? So I give you mu is here. This is the drawing that I give you here. So mu 3.8 to 8427. So because this is very sensitive, so you will get a lot of numbers in the back of decimal. Okay? So try this number. Okay, and then initially you set 0.7. What will happen? So you see, if you set 0.7, I try. Okay, it will become, first time is like this, and then suddenly constant, right? Did you get it?
Mu is 3.8 to
3.828427. And then the y0 is 0.7. Okay, and then now you change the initial value. Okay, the mu does not change. You only change the initial value. So instead of 0.7, you make it 0.71. The behavior of the system changed drastically just because you change the initial condition. Is that so? Yes. So you can see this is what is called chaos. Yeah? Very sensitive to initial condition. Yeah? Sensitive to initial value. Okay. And of course the parameter. Right. So try this. Mu is 4. Exactly 4 now. Okay, mu is 4, and then now you change the okay, initial value. Okay, you can try initial value of 0.2, right, and then 0.21, and then 0.001, and so on. Okay? And if you plot this, okay, check the difference. How the initial value change, okay, very small, right? The change is very, very small, isn't it? Okay, and how they actually become greater and greater, yeah, over time. So this is what I did. So here is initially 0.2 and then 0.21. Okay, and then I calculate the absolute difference. So this is x1 and this is x2, the red one. Okay, and then if we change to 0.002.2001, okay, and you can see it changed a lot. Yeah. So it will first start, the beginning is the same, right? The beginning is the same, and then after 7 iteration, it will start to separate. Okay. Now, if you make it a lot of zero in the back, okay, see, in the beginning again is almost the same, okay, but after 15 iteration, it will change a lot, okay, and so on. Right? So here in the beginning, yeah, if you have a lot of zero in the back here, in the beginning is the same, right? Okay, after 20 iteration, it will start to change behavior. So what does it mean? Look, if you create a difference equation, okay, and this is actually contains some chaotic behavior, okay, means sensitive to initial condition, right? And then you are happy, right? Say, we don't know, in this example, it's only 20, so you can observe. But say you plot only 15, right? And then you will say, it's okay, no problem, it's the same, right? So then you will say, okay, it's the same. But you did not plot the rest. Okay? And you will see that they are actually different. Very sensitive to initial condition. Can you see that? Right? So it's the sensitivity, yeah, sensitive dependent on initial condition. Okay? So dynamical system that is sensitive dependent on initial condition, that is called chaos. Yeah? So if whenever you take two value A1, 0 and A2, 0, which are close together initially, right? And then A1n, n is, that means n must be larger than 0. Eventually it will go farther and farther apart. Yeah? So there is a small number that actually make them some distance between them. Yeah? So that one, yeah, dynamical system that sensitive dependence. Yeah? So we must choose a sensitive constant epsilon here, so that there is a certain interval containing that value. Okay, so that is to verify that that dynamical system is sensitive to initial dependence. So, this is another example of well-known function. Okay, it's not logistic. This is called Baker function. Again, this is a difference equation, you see, but this one is based on the value. Yeah, if the value of Baker function is between 0 and half, okay, and the next Baker function is 2. Okay, if the value is between half and 1, okay, then this one is 2 Baker function minus 1. Okay. So with initial value of 1/3 and then 0.3333, okay, it will have different result. So normally you will say 1/3 and 0.3333 is the same, isn't it? Right? But when you put it into Baker function, it's very sensitive. You can see the absolute difference. Oh, yeah, initially is up to 9, they are the same. Okay, but up to that, it will behave very much different. Okay, so that code that you mentioned a while ago, okay, contain the computation of Lyapunov exponent, isn't it? Right? So this is another method to describe that separation a while ago. Yeah? This is the separation, right? So Lyapunov exponent of a dynamical system with some initial condition. This is this function. What is this? The ln of the first derivative. Yeah? And then you take the limit to the end, to infinity. Yeah? So this is say example in that logistic map a while ago. You get this function, right? And this is the fixed point, okay? And then you get the first derivative, right? And then if you put it into the Lyapunov exponent, you will get this lambda value, okay? So, okay, so the Lyapunov exponent can be considered as the average loss of information of the successive iterates point near the dynamical system. Yeah? So if the two initial values are close, and after the iteration remain close together, then the Lyapunov exponent is negative, yeah? Because of the logarithm. Okay? By contrast, if the iterations separate from one another, okay, the Lyapunov exponent is positive. Yeah? So if the Lyapunov exponent is positive, you know this is probably chaos. Is that clear? So this is the Lyapunov exponent is the one that one number, okay, that determine it's chaos or not. Okay, so how do you know? Okay, if the Lyapunov exponent is positive. Okay, so here with that you will see definition of chaos. Yeah, this is probably the last one. So dynamical system is chaotic if it satisfies at least one of the following conditions. Yeah? One, the dynamical system has positive Lyapunov exponent at its point, okay, that is not eventually periodic, okay, or a dynamical system has sensitive dependence on initial conditions. So that is the definition of chaos. Okay, with that, I think yeah, this is just make it more stronger. Okay? So we finished the very long lesson. Okay, so this is what you have learned today. I hope you can see the summary. Okay. Is there any question? Okay, I guess. Yeah, a lot of things you learned today, right? A lot of concepts.
Yes.
Okay. Usually I give this 6 hours, but we can finish it very fast.
Oh.
Oh, including that practice, no? But this one will.
Oh, okay. Yeah.
So I hope you can try on your own, and because this is very interesting topic. And my suggestion again, you join the Santa Fe Institute courses. For...
Oh, but you say it's difficult.
No.
It's like,
There are some difficult, there are some easy. So you
oh, okay.
join the easy one first.
Okay.
Okay.
Oh, it's free, right?
It's free. It's free. So even if you don't finish it, it's fine. So, but if you finish it and your grade is certain numbers, I think below 80 or something, then you will get certificate.
Oh, okay.
Okay. Look, you get certificate from Santa Fe Institute. You know. Right. So you can be proud of.
Okay. So I'll check Santa Fe stuff.
Yes. So this is like one of the best institute in the world in terms of complex system. Okay. So great. So see you tomorrow.
Okay. See you tomorrow, sir. Thank you.
Thank you.